can always follow him on social media as well. And more importantly, Rob is somebody a lot of young researchers in the community and even not so young researchers like me really look up to. And we're also proud to say that he is an alumnus of IIT Madras. And so thank you, Professor Rob, for accepting our invitation to come and talk to you. Over to you.
Can you hear me now?
Yes, we can.
Okay, great. Let me try to share the screen. Just give me a second.
Oh, I love your "Make AI Great Again" cap on the desk.
Yeah, that should come along with me. Yeah. Okay, are you able to see my slides now? You should be in a minute. Yeah, there you go.
Yes, yes, we are. Yeah.
Okay. Let's see if we can get started. Okay. So yeah, I am Rao Kamampati, as Ravi just introduced. Thanks for those kind words, Ravi. So let me just put this timer. Stop watching. Okay. So today I'm going to talk about explainable AI, sort of a unifying interpretation and a framework. So just before I get started, so that's my my background is okay. So you are not actually are you seeing the next slide?
No, we are just still seeing the title slide.
Okay, there is something wrong. I probably am not sharing it correctly somehow. Huh. I don't know why it's not. Just give me a second. There is something wrong with. Okay, stop share. And let's try again. Yeah, so now you can see the next slide, right?
Yes.
Okay,
Yes.
thank you. There's something went wrong. Okay, so my own background is that I have been working of late on human-aware AI and human-AI interactions. How do AI systems interact with humans, either on one-shot decisions, such as just a classification decision, or a sequential decision where there is like a behavior that is being exhibited by the AI system with the human in the loop. And so essentially it could be a collaborative scenario or a user being an observer and so on. So our setting typically involves collaborative problem solving where AI agents provide decision support to the human users in the context, typically in my case, of explicit knowledge, sequential decision-making tasks. I will talk more about that distinction in a bit. And then we have sort of focused on proactive explanations based on model reconciliation, which is another thing that will become clearer as I go forward. And we sort of use this in both embodied human-robot interaction scenarios as well as decision support scenarios. And most of the work that we do is typically given with respect to, is evaluated with respect to systematic human subject studies. One of the big problems about humans, human AI interaction, talking about explainability, is people tend to think that I am human, so I know what explainability should mean. Engineers considering themselves human is a bit of an oxymoron in my view. So essentially, we do really require some careful evaluation of our approaches. So we do that with respect to, systematic IRB approved subject studies. I've done like a bunch of things around this. There is an AI magazine paper on challenges of human-aware AI. There's a book that's coming out on explainable human-AI interaction, a planning perspective. And then I also gave like a, most of the work, of course, is done with my, great students, including Tadagata here, who graduated a couple of years back, and he is in the IEEE AI 10 to watch list this year. And then, of course, Sharath and Anagha, whose work I'll be talking about here too. So I have technical talks on exactly what we do. And in fact, there's one here on getting AI agents to interact and collaborate with us on our terms that you can look up on YouTube, that just at most a month old, and it should be quite faithful view of what we do. So this is what I thought I'll just do when Ravi asked me to give a talk, except for some reason, Ravi had a different idea. He thought that I should earn my keynote. So he said, you have to make a new talk and make it more of a tutorial version of sort of a different perspectives on explainable AI. So that's what I am trying to do today. So basically what I, as I said in my abstract, essentially, I want to kind of talk about not just my work, although I'll use my work to get the points across, but I want to look at the bigger picture of explainable AI. And there are different tribes, and they're all looking at this process, this issue of what does it mean to have explainable AI systems in very different ways. And so even though there are papers like all over the place in AI on these topics, oftentimes they look and surface as sort of incomparable. And so what I'll try to do today is to sort of tease out the unifying themes and point out essentially that they're all doing the same thing, except maybe with more versus less assumptions. So that's what I am trying to do. It's a bit of a sort of a informal teaching oriented talk. As I said, if you are more interested in exactly what we do technically, you should look up one of my other talks, which is on the YouTube. So let's get started with that. So explainable AI, of course, has like multiple tribes. Basically, there is the thing that I guess the person who was just talking before me, as well as maybe other people, speak about explainable machine learning, especially explainable classification, for example, which is essentially oftentimes a tacit task where the system essentially has figured out how to classify with its own internal representations. And so there is really not too much of a shared vocabulary between the system and the human. And so when you ask the system, why did you think this was an Alaskan Husky, as for example, that top example is, since the system doesn't have any features that are feature-based vocabulary that is common with humans, it basically has to resort to the shared substrates. Typically, the shared substrates are the image or the space-time tubes, as I would like to call. Images are the ones that people kept looking at in explainable machine learning framework. So in the cases where the classification task is a tacit task in the sense that there really is no shared vocabulary, typically explanations have been saliency explanations, like basically pointing out pieces of the image, are, in the general case, it has to be, pieces of the space-time tube that you would say are somehow relevant. You, the AI system, would say are somehow relevant to your decision, and the humans will try to make whatever they can of it. Of course, there can be explainable classification when it's kind of feature-based, where there are symbolic features that people do understand. There are people who are doing that too. Obviously, in many, many machine learning scenarios, actually, human understandable features, right, are actually quite important as a bridge. And in those cases, the explanations are typically in terms of feature weights, attributions, and so on and so forth. So that's one type of tribe. There is a bunch of explainable behavior people who are into, typically they tend to be in the human-robot interaction community. There are conferences on it like HRI and so on. They look at either tacit interactions where the AI system or the robot and the human are basically interacting without talking to each other, without directly communicating in any explicit linguistic means. So in that sense, the behavior itself is the signaling mechanism for communication. So no shared vocabulary other than the observed behavior. In those kinds of scenarios, explainability typically means predictability. You know, the robot is doing what I'm expecting it to do. Explicability, it did exactly so predictability is I know what it will do next. Explicability is that it is doing what I'm expecting it to do. Legibility is the robot or the AI system sort of giving you a heads up as to where it is going, you know, again, without necessarily using any linguistic means, just by behavior itself. So for example, the usual example in the robotics community is if there's a goal 1 and a goal 2, and you know, the robot is trying to go to goal 1, the legible way of doing that is to go towards goal 1 from the beginning rather than go all the way to the middle and then last minute turn towards one goal, because that makes it hard for the human in the loop to figure out which particular point you're trying to go to. You can also have explicit interactions. Of course, human-robot interactions don't have to be just tacit level. The lower level interactions tend to be such as motion, etc., tend to be sort of, you know, tacit interactions. But there can also be explicit interactions where the robot gives explanations as to why it is doing some decisions as against other. In these cases, obviously, oftentimes the explainability is achieved with symbolic explanations. And then finally, you know, there's the kind of work that I do sort of, you know, straddle some of these worlds, explainable behavior in the planning decision-making sense, where typically the planning part tends to be with explicit knowledge tasks, with symbolic models. And so with respect to the symbolic models, you are providing explanations for your decisions. So these are the different kinds of things, at least, that are available in this explainable AI community generally. And papers on these sorts of things are published almost in all AI robotics venues, and they're different enough that this, you know, blind man and elephant problem comes. So what I want to do quickly is give some sort of sense of why they differ. And to some extent, I want to do that by appealing to your own sense of when you expect explanations from your friend when you're interacting with them. So let's start with, why do AI systems have to even give explanations? A certain famous researcher in the Facebook AI has sort of remarked more than once that, look, explainability is unnecessary. Facebook makes millions of recommendations per day and no one asks for an explanation. You have to keep that in the back of your mind. I mean, my answer for that would be that the kinds of recommendations, that the decisions are so non-critical that people don't necessarily care about asking for explanations for them, perhaps. But certainly in many scenarios, we do expect the machines to provide explanations for the decisions that they're making. So for example, you'll have internal self-explanations that systems might be using within the AI community. These have been used, explanations have been used to guide search. Explanation-based dependency-directed backtracking is really explanations, is in machine providing explanation to itself in its own, with respect to its own models. And then explanations can also guide learning. This is a very well-known idea. Again, some of the people might remember that there was a whole entire area called explanation-based learning, where essentially the machine tries to explain to itself why the particular instance has the label it has using some partial background theory. And then the features of the instance that take part in this proof, are where the explanation becomes sort of a proof with respect to the model, will be the ones that are relevant. And so that sort of becomes a feature selection problem. So this is one way explanations would be useful within the system itself. They can also be external explanations. To some extent, that's the one that we are mostly interested in of late. When people talk about explainable AI, you're talking about the explanations that the system gives to other agents. It could be the other AI agents. MAS community, AMAS community is typically interested in this sort of thing. Offering proofs of correctness of decisions can be part of that in external explanations. But the one that I'm really mostly going to focus on in this talk is to the humans in the loop. So there is a human in the loop and the machine is making a decision and the human is expecting some explanations with respect to those decisions. And in those cases, machine just talking to itself saying what I said makes sense to me because of my, let's say if it's a neural network system, because these weights are the following numbers, that doesn't at all constitute a reasonable explanation for the human in the loop because they have no way of understanding that model. So explanations in those cases cannot be a soliloquy. It cannot be the machine talking to itself, even though in the internal explanations, they are very much a soliloquy. Unless humans have no life but to understand systems mutterings, which it turns out apparently in machine learning community, typically people tend to have the explanations as just a debugging issue. And so they kind of spend their lives trying to understand the machine's representations. But in most normal scenarios, you want to provide an explanation to the human in language that the humans can understand. Explanations also depend on the role of the human, of course. Is this human a debugging human who is actually trying to debug the system just so that it will work correctly? Or is it an end user who have no interest in trying to change the system? They just try to make sense of what the heck is this system basing its decision on. And in those cases, saying, look, read the big manual or look at my code base is not an explanation. You need to provide an explanation that is succinct and it can make sense to the human in the loop. So XAI has mostly been about explanations for humans in the loop, but it's typically often, unfortunately, confused. Even though XAI is about this, it tends to get confused with these many a time. And so you may want to keep your eyes open for that. Whenever they have systems talking to themselves and expect that humans to understand, then you are essentially sort of going against the whole grain of AI, which is AI is for machines to come into our land, not for us to lose our lives and go into the machine's land. So keep that in mind. So use cases for human in the loop explanations. You can have a debugger trying to flag and correct the system's behavior. You might have a lay observer basically just looking at the behavior of the system, an expert observer looking at the behavior of the system, trying to make sense or to correct it, a collaborator who is taking a part in some collaborative task along with the system, a student where machine is in a teaching role. So the machine is trying to explain to a student in the loop. In fact, explainable AI was first studied way before anybody talked about it in the context of intelligent tutoring systems. So essentially, you are kind of giving explanations to the student in the loop as to why they should do this step in this way as against a different way. And so similarly, the human in the loop can be a teacher with the machine in a learning role. And that sort of brings in sort of teaching to the machines. What's the best way humans can teach to the machines? And they also explanations wind up becoming quite important. Also, the tasks where the explainable AI systems are used tend to differ. That serious differences are, one is that they can have one-shot versus sequential decisions. Oftentimes, most of the classification decisions are just one shot. You just provide what the label is, and the human likes it or doesn't like it. If it doesn't like it, they will ask, why the heck did you come up with that particular label? Sequential decision, you are essentially showing a behavior, and the humans may be surprised at some parts of the behavior or maybe okay with the whole thing. That's the one big difference. The other big difference tends to be interactions themselves. Is it a one epoch? That means that is the human just going to interact with the machine once, either on one shot or a sequential decision task, or is it a longitudinal one where the human and the machine coexist for quite a long time? The second part is important because, as I'll tell you, as I'll bring up later, you typically ask explanations with humans that you don't know. And when you become familiar with a particular human, particular friend, you reduce the need for asking for explanations reduces quite significantly because you have sort of understood a lot more about the other person's model. And so you can make sense of their behavior much faster without having to ask for explanations. Okay, that sort of brings us to when and why do humans ask for explanations from each other. So the idea, of course, is that there's some different times when I'm just asking you to think about yourself. When do you ask for explanations in your own life? from other people, not necessarily with the machines, because that will sort of set the stage for what sort of work we need to do. And I'll sort of connect it to the kind of work we do as well as what other people do. So when we are confused or surprised by the behavior of the other person, it's not what we expected the other person to do, and it's inexplicable, so we want an explanation. Note that the confusion is orthogonal to correctness and optimality. It's not whether the machine did the right decision, whether the other person did the right decision. But if you didn't expect them to do the right decision, then if they do it, then you would be surprised equally. So for example, you would be confused and surprised if your 2-year-old nephew is able to give the exact distance between Earth and Sun in kilometers, for example, because you don't expect this little bozo to know so much information about astronomy. And so you would be surprised and say, hey, where did you learn this? So because your expectation was violated. Explanations here, in general, help reconcile the expectations. So if your little kid's brother tells you that the nephew says, oh, the other day, the dad was muttering this to themselves and I just memorized it, then that sort of changes your model of this kid. Okay, so the second other different place where we might want explanations is when we want to teach the other person and or make sure that the decision that the other person made is not a fluke, and that the other person really understands the rationale for their decision. So you're almost like in the teaching mode. In fact, I set up exams where I'll have a true-false question and say justify, and the answer, the marks that you get on that question depend very much on the justification. Even if you get the true-false right, if you justify it wrong, you lose a lot of points. That's because I'm trying to understand, did you guess by tossing the coin, or do you have an understanding of what the statements, in coming to the decision about the truth and falsity value of that statement. So in this kind of case, you're using the explanations to localize the fault of the other person's model. Then there is the two other general points, which is noting that the need for explanation itself is dependent on one person's model of the other person's capabilities and reasoning. So it's not about what you know about the world. It is about what you think the other person knows about the world. That makes you either be surprised or ask for explanations. The only time these models will be the same is if you somehow are one of these people who have not achieved social intelligence and assume that everything you know is exactly what everything other people know and believe. That obviously is not, the case. And so we are always looking in terms of the explanations dependent on other person's model and also their capabilities and reasoning. And finally, explanations are connected to trust. And so we ask fewer explanations from people we trust. And so that's sort of a bad explanations reduce trust, good explanations increase trust. And when the trust is increased to a certain level, you may not even ask for explanations. You might sort of decide, well, I don't know why they're doing it, but they're normally right. So I'll just leave them to, do their thing. This is sort of, correct informally from with respect to your own, interactions with each other. So now when the next thing is, how do we exchange explanations? How do humans exchange explanations? One way we exchange explanations is actually, in fact, the pointing or tacit explanations. You typically don't do this as much, but you used to do it when you were a little kid. And if you have little kids and they don't know how to speak, you realize that they'll do all sorts of gestures to point out to things. So pointing explanations are pointed to specific features or regions of an object or image in the space-time tube or in the single image that you have. It's feasible sometimes for one-shot classification decisions on spatial data. So just sort of pointing to the right parts of the same object, to kind of say, this seems to be the important thing. So for example, this is a red striped butterfly because, and then you show the piece of the image. And typically these are very useful when the task under consideration is tacit, in the sense we don't have symbolic vocabulary to describe. So oftentimes, the birding books, for example, typically are full of pictures and annotations because they're not that much common vocabulary that everybody has developed about how to differentiate one bird from another. But these kinds of explanations also tend to be quite unwieldy. They are high bandwidth and high cognitive load, especially if you're trying to use these sorts of pointing explanations for explaining sequential decisions on spatio-temporal data. Because as it will involve pointing to relevant regions of a space-time tube, it's not just a single image, but it's essentially a sequence of images flowing through the time. And you sort of have to talk about that whole region. So for example, if I say, I'm trying to answer, why did I take this earlier United flight? You asked me, why do you take this earlier United Airlines flight as against this later one? I can't just show a single image and point to it. I actually have to, in general, point to my space-time tube of my life in the past several days or something and say these pieces wound up being important in making my decision. So keep that in mind when you get too enamored with saliency-based explanations that have become popular in machine learning. The other kind of explanations, which are sort of what we typically think of as explanations, are symbolic or explicit explanations. These are feasible for both spatial and spatio-temporal data, and also for one-shot or sequential decisions. Of course, the downside is that they do require that the humans, exchanging the explanations, share a symbolic vocabulary or learn one to get by. So oftentimes when, for example, there are two people across two very different languages, wind up trying to communicate on a single task, they might first start with some kind of pointing explanations like primitive cavemen, and then slowly they will develop common vocabulary and they will start exchanging explanations in this common vocabulary. And the interesting thing is the common vocabulary is this way of providing the saliency regions either on the image or on the space-time tube in highly compact form. And when you're doing it, these symbolic explanations essentially reduce cognitive load on the receiver. And even though, in fact, after hearing the explanation, the receiver, in essence, sometimes has to recreate the space-time tube with the annotations in their own head, it turns out it's easier to do that than to go through the other agent trying to show the annotations on the full space-time tubes. This is an important part to keep in mind. The symbolic explanations are not only compact, but also reduce the cognitive load on the receiver. The reason you talk to each other in language rather than by gestures is because it actually reduces the cognitive load on each other, even though there is all this uncertainty, etc., that does come because of any linguistic uncertainty. Typically, pointing explanations are used for tacit knowledge tasks, as I pointed out, and symbolic ones have been used for explicit knowledge tasks. However, as I mentioned in my example, over time, we tend to develop symbolic vocabulary for exchanging explanations, even for tacit knowledge tasks. I don't know how many of you are basketball fans. I'm not a big basketball fan. My son is into basketball, so I sort of know some things about it. But basketball, I would say, is a pretty tacit knowledge task because it's not, the way you actually play it, it's a really physical task, and it's not just, something that you can talk in symbolic terms. However, when you're explaining some players' moves in that, you see, if you're seeing the sports, typically they'll put saliency regions on the TV about the regions, but they also use terms on like things like in basketball, it will be pick and roll basketball. If you asked me to do this talk about 40 years back, I would have given you cricket analogies, but I've forgotten all my cricket analogies. So I'll give you the basketball analogies. So pick and roll is essentially a symbolic term, which sort of signifies a whole bunch of space-time tubes with annotations. And that sort of makes the explanation way compact. And that's a very interesting thing to keep in mind. So now what are the requirements of the kind of explanations that we sort of exchange? They need to be comprehensible, cognitive load in parsing the explanations. Is the explanation in a form and level that is accessible to the receiving party? Communicability, which is the ease of exchanging the explanation, which, are you giving your entire brain? Are you giving symbols, for example? Soundness, this is an interesting question. Is there a guarantee that the explanation is somehow correct? A whole bunch of people in Explainable AI are somehow stuck with this idea that there's this notion of correctness. At best, first of all, notice that the soundness is only with respect to the agent's model, the explainer's model, and the explainer's model may well be already faulty. So with respect to that, it can potentially be sound, but you're also allowing, when people give you explanations, they don't necessarily have to tell exactly the explanation that is sound with respect to their model. They oftentimes might give you explanation that you would like to hear. That leads us to the satisfaction part, which is, are you satisfied with the explanation? If you ever did any kind of, telephone customer service, at the end of which they'll say, you'll ask, why did you charge me this much? And then the other person will give some kakamimi story. You're not happy. You'll ask some more questions. They provide some explanations. At the end, they say, are you satisfied with our explanation? Really, you only will be satisfied if they give you your money back, right? Essentially. So in general, actually, satisfaction with the explanation is a slippery slope, because satisfaction is the way system will learn, we also learn to tell sweet little lies to each other rather than sound explanations. So you should be very careful if you ever hear of people talking about, I'm doing end-to-end explanation learning. If you learn end-to-end explanations, then you are learning what makes people getting those explanations happy, which has nothing to do with whether or not they're actually sound. That's something useful to keep in mind. In fact, my biggest nightmare right now is that what if, so European Union has GDPR, right? Generalized data protection regulations. So basically that gives you right to ask for an explanation. So the question is, what if somebody just trained some machine learning system which just gives the sweet little lies that you want to hear? So some sort of a GPT-3 generated explanations for when you are asking for why did you do this decision. And oftentimes people might be satisfied with that. And that completely shortcuts any connection to actual tasks. So it's useful to remember that satisfaction with respect to explanations is a slippery slope. Okay, that's a long setup to what I want to bring, which is that the right way to think about explanations in respect to humans and machines is to think of explanations in terms, is to do this the way explanations work in the human scenarios. And so my answer as to what does it take for an AI agent to show explainable behavior in the presence of human agents, the answer is managing mental models. Remember, I kept talking about the model of the capabilities of the other person, for example. So everything is with respect to the model you have of the capabilities of the other agent. That based on that, you get surprised, and based on that, you want explanations. So managing mental models becomes very important. For those few of you who may not have heard about this, and also I know IIT is an engineering school, so it is possible that there are people without social intelligence in IIT. So let's talk about Salian test, which is the point which is sort of used to talk about the importance of social intelligence. Basically here you have in this picture, Sally, you have in this picture, Sally in the red shirt and Anne in the blue shirt. Sally comes and puts the ball in the yellow box. You are looking at all this, you the observer. Okay, Sally puts the ball in the yellow box and goes away. Then Anne comes in, takes the ball from the yellow box, puts it in the gray box, and Anne leaves. At this point, Sally comes back into the room, and I'm asking you, the observer, where would Sally look for the ball? Okay, and typically, I'm hoping, first of all, that you all know the answer. If you don't, certainly you should get your social intelligence checked. But it turns out that kids come into this world in the beginning thinking their whole body is connected to the rest of the universe. They'll sort of realize after a while that the body is distinct from the rest of the universe. And then for a while, they keep thinking that what they believe in is what everybody else believes in. And at that time, which is like below 3 years age, if you give the Salian test to kids, they tend to say that since they know that the ball is in the gray box, Sally must know too. So Sally will look for the ball in the gray box. After 3, if you ask them, they will basically tell you the right answer, which is that yellow box. And after 4 or 5, if you ask them, they'll basically give you a tough look saying, why are you wasting my time? Don't you have anything better to do? And when they realize this is when they realize that the mental models of different people are different. And that actually opens up the whole capability of telling lies. I joke around that when my son when he was young, when he told his first lie, I was ecstatic because I knew that he has a working brain and he was able to do salient test right in his own brain, because he basically realized that what he knows and what he knows and what I know are different. And so he can use that to his advantage. So lies are essentially using the same distinct models. Explanations are also using the distinct models and using that to make sense of your decisions. So managing mental models winds up being important. By the way, that's just a funny Friends episode that if you have time, you can watch it later on, where they go into this multi-level regression of mental models, where Phoebe is saying, they don't know that we know that they know that we know. And this level of high, significant levels of recursion might actually be required in the worst case in the mental models. But the good news is, I'll tell you today that most of explainable behavior is just based on just 2-level recursion. That's it. Okay, so that is the more or less the big point of my talk today that I'm going to get across to you, which is that I'll look at the more general scenario, which is the sequential decision setting, because one-shot setting is, like the machine, the classification, etc., are simpler scenarios. So we'll understand this one, and then the other ones will be sort of special case. So let's start with the scale of the 3 models, essentially. So if you have just an AI agent, which is sort of trying to reach some goal in its world, then it has its own model, MR, R for robot, which is basically it's using to decide its course of actions. And then the moment there is a human in the loop, then the human has their own model of the task, their own model of what their goals are, and so on. And so there is an MH, and the AI agent now all of a sudden not only has to think about its model, but also has to think about humans model MH. And since it doesn't have humans model directly, it needs to estimate the humans model. And let's call that estimate MHR. So that robot's estimate of what the humans model is. And this robot's estimate of what humans model is what you have typically heard of oftentimes when you think of robots or AI systems anticipating what you are trying to do and completing your sentence or completing your task and so on. So, recognizing intentions of the humans is basically based on MHR, which is the robot's understanding of the human's goals and actions and so on. So you can also basically the human, in this case, you can also, in the second one, the robot can also kind of give more information to the human by projecting its own intentions. In this case, in this demo, they're being done in the HoloLens, but that's important for our talk. But the bigger part is the problem with humans is the moment the humans come into the scenario, they always anthropomorphize. That's just the way we are. So the moment humans are in the scenario, they will also essentially come up with an estimate of the robot's model because they're interacting with the robot. So they sort of make some cognitive theory about what the robot's model of the task and its goals are. That's MRH. And then at this point, the robot not only had to already need MHR, which is the human, its estimates of the human's model, it now also needs its estimate of what human thinks about its model, which is MRH hat. This MRH hat is like the most important thing in terms of explainable behavior, as I'll point to you in a minute. It turns out that MHR and MRH are expectations on the models. And as I mentioned, MH and MR themselves are the humans and the robots models of the world. And so they're sort of independent. MH and MR are independent. MHR and MRH are sort of loosely cross-correlated because to the extent the estimation is good. Okay, so now why does this MRH actually wind up changing how the behavior between the human and the robot or the AI system get affected? So when the robot's task model differs from the human's expectations of it, that is MR is different from MRH, the plans that are optimal, the behavior that is optimal with respect to the robot may not be so in the human's expectation. At that point, you have two options. One is, say, I would forget about my model and do what you expect of me, which is explicable behavior. So do what people expect you to do. You never have to explain oftentimes, unless they are in a teaching scenario and they, after you say true, false correctly, they ask for justification. Typically, end users are happy if the behavior is explicable. If that doesn't, if that is oftentimes explicability can be quite costly. If that is costly, then you provide explanations as to why you have to make a different decision. And that explanation is in terms of the differences in the models. So an example that I want to show you here quickly is sort of, again, this is an embodied scenario. There's a human commander and a robot on the search and rescue scenario. And so the beginning, the map of the environment is shared by both of them, but the robot is actually on the ground. And so it might actually find that certain paths have gotten closed because the rubble has fallen. Maybe it turned out that that particular path where there was that obstacle, that was the fastest path. But it turns out that that's what the humans might be expecting. But the robot, to be explicable, has to make that path actually clear and go through it. Okay, that's what it's doing here. The first time around, it is actually making the path clear and going through it. That's being explicable. If you do that, in essence, the behavior is as expected, so the humans are not going to ask for explanations. The other case, of course, is that this going through this particular SAD is costly, so the robot essentially decides to take the next best path. At that point, it needs to say why this is better, in terms of how its model of the environment right now, the map, how this map differs from the human's model. And so it needs to sort of provide the minimum change in the model. And so if you actually, the wording there is, it basically says that this particular path is blocked. And once you make that change, the human makes that change to their model, they will realize that the robot's behavior is indeed the optimal one, because this path is blocked. So the second best path will become the best path. So it turns out that if you think in terms of these three model explanations, the requirements of explanations are actually reasonably well satisfied. Cognitive load in parsing explanation comprehensibility will be in terms of this model differences that are computed. Communicability is just sending the model differences. Soundness, I'll show you in a minute that in fact these model differences are computed by the machine starting from its model and trying to take it towards the human's MRH. And so that's how soundness is satisfied. And satisfaction, we won't talk about it right now because as I told you, it's a slippery slope. Some other insights from the three model account is that surprise happens when the robot's behavior is not consistent with what human expects. That is, MRH is different from MR. Notice we're not talking about MH. We're only talking about MRH being different from MR. You're not surprised at people because they're not like you, unless you're a narcissistic, crazy person. You're surprised at people because they're not behaving the way you expected them to behave. So explanation is an attempt by the AI agent to get MRH close to MR. And MH and MR are independent. And as I said, MRH and MHR are loosely cross-correlated. In many special cases, and this is what sort of the connection to the other areas come, some of these models can be assumed away. If, for example, the AI system assumes that MRH is MR, then explanations can be soliloquy. So for example, if the AI system assumes humans have no life, they will act as if my model is their model, then it can just talk about the correctness of its decision with respect to its own model. This is sort of what happens in all the debugging explanations in machine learning, because the machine essentially is just showing the saliency regions that wound up being important with respect to its model and its own decision. It has no understanding of what humans' model is. All that is happening is they happen to share this primitive common substrate, which is either an image or a space-time tube, and they're using that to show the explanation for your decisions. Similarly, if the AI systems assumes that all MRH are identical, that means all humans make the same assumptions about the AI system's capabilities, then it can sort of compile that away into its reasoning. This sort of happens oftentimes in robotics community, for example, when they assume that all humans expect robots to move in straight lines, for example. If you can make that assumption, then all the robot needs to do is to provide an explanation whenever it is not moving in a straight line. So in essence, the reconciliation is with respect to whenever you are no longer in straight line. That's only because you made this meta assumption that humans expect straight line motion as the MRH. And finally, the other thing that relevant to this is model reconciliation focuses on local explanations in as much as it aims to reduce the difference between MRH and MR to make the current decision and the current example interpretable. If you want to go beyond the current example, then you will start talking about global explanations. And in the worst case, this is what has been called interpretable model as a whole. That is sort of like saying, look, here's my brain and make sense of it, which again has huge cognitive load problems. No end user ever requires anything more than a local explanation, and which is with respect to the MRH and MR differences with respect to the current example. And remember, I talked about when and why do humans ask for explanations from each other. It turns out that the various things that I brought up essentially can be talked of in terms of MRH and MR. For example, the correctness and the confusion is orthogonal to correctness and optimality. It only depends on the expectations. And so it only depends on MRH and MR, not MH and MR. Similarly, explanation is reconciling expectations. So which is explanations will wind up getting MR closer to MRH. I'll show you an example, but basically that's sort of model deltas. And finally, when models get reconciliated, there is less need for explanations in subsequent interactions. And so explanations are needed only when MRH and not MH is too different from MR, and they are customized to MRH, so that in some sense they become customized to the user in the loop. And then every time an explanation is given, in general, MRH will be updated, if the humans are paying attention. And so as time goes on, they will have less need for explanations. So Ravi, what should I do in terms of time? Do I have can I take another few minutes, another 5-10 minutes, or should I just stop and take questions?
Sure, maybe another 5-10 minutes. The next talk is at 8. So
okay, then let me try to take a few more minutes and just try to complete this thing. So explicable plans, I mentioned that explicability. So it turns out the way the machine can do this is to sort of take into account not only the cost of the behavior with respect to its model, but the distance of the behavior, optimal behavior, from the behavior expected by the human. And if you do that, you can provide explicability. We have papers on that. Explanations themselves wind up basically saying what should be the epsilon, the delta, the model difference that should be added to MRH, such that the human would realize that the optimal behavior or the decision by the robot is actually the correct decision, even in this new MRH plus epsilon. And to do that explanation construction in general, in the most general case, you have to do a search in the space of models. And so we actually do this model reconciliation as a search in the space of models. And basically, the way the model, the explanation will sound is because the robot essentially is trying to start from MR and take it towards MRH, or start from MRH and try to compute what delta should be added such that the current decision will make sense to the human with that delta added. So you can do this bidirectional search, but as long as the robot is faithfully sticking to MR and MRH as the endpoints, then the explanations are sound. It turns out that one other issue is that, I mean, I have too much time to go into, is when you just provide the model difference, you are expecting the human to have to come up with the inference, figuring out that in the new model, the current the behavior that the robot is showing is the optimal behavior. Depending on a sequential decision task that you're looking at, that could be a quite costly inference problem. So the way you can sidestep that is to actually split that into demand-driven explanations, where the humans ask not just why, but say, why did you do this? Why not this other decision? And so the humans provide a foil saying, why aren't you going through corridors A1. And then that file, that becomes a file. And then the robot then really has to explain why corridor A1 is not as good as corridor A2 that it wound up taking. So this is called file-based explanations. And we actually do a whole bunch of work in just file-based dialogue. And that too can be understood in terms of model reconciliation. It's just that you're reconciling with respect to just the file rather than with respect to the entire example decision. So it turns out that this is used in decision support systems between humans working along with a planning decision support system. I'll not go into too much detail on that. There's a variety of extensions that you can do to this 3-model thing. You can do, I didn't really talk about the model representations, other than saying maybe they're symbolic, but we typically tend to use planning action precondition based models, but they can be extended to other kinds of models. They can be related to other formulations of interpretable behavior, such as legibility, predictability, and so on. This is something that should not be surprising to you because I started by pointing out how they are connected. And handling files and models at different levels of abstraction can be handled because different users in the loop might have different levels of abstraction. So for example, a doctor explaining a diagnostic decision to their patient will use a different explanation than when they're explaining the same decision to the other doctors in the office, because the models are at very different levels of detail. And so you need to take that into consideration. The reconciliation is with respect to MRH that you have to keep in mind. And we can consider multiple human agents. You can consider also vocabulary differences. That is something that we'll spend a little bit of time on before ending. And then just before doing that, I also want to point out that this whole idea of connecting explanations to models, mental models, which is what they are, makes it clear to you that explanations are connected pretty closely to trust and deception. Mental modeling can be used for interpretability as much as it can be used for deception and obfuscation. You can actually do lying with respect to mental models, and I'll show you that in a minute how that can be done. And in general, if you engender trust in the human, then they're less likely to ask explanations or expect you to show explicable behavior, so your life becomes easier. Those of you with PhD advisors know that after the advisors trust you, they don't ask you, where were you over the weekend? Because they know that you're doing things fine. In the beginning, they might ask you, right? So again, this sort of brings up a whole set of ethical quandaries. In particular, many of these ethical quandaries and explanations are connected to satisfaction. People are satisfied with an explanation. People being satisfied with an explanation has nothing to do with whether the explanation is sound. And so, in fact, we have done work showing that within the model reconciliation framework, the machines can provide lies of omission as well as lies of commission. All that means is, remember that search that I had from one model to the other model? It turns out that you essentially, instead of starting from MR, the robot starts from a different model, made-up model, and sort of reconciles that to the human's model. And so that sort of is a lie of omission. So you can provide lies, and that actually we did some testing on how people will handle white lies if they know that the white lies are being told by the humans in the loop versus machines in the loop. And those of you are thinking, oh my God, lies are not good. You know that the society will fall apart if we don't tell white lies to each other. Like if somebody asks you, how do I look? Please don't tell them, these are all the problems with your face. You're supposed to say, you look great, right? So that's a bit of a white lie that we do. And so in fact, the question is, you could have personal assistants telling us white lies to get us to do things that are good for us. Do we want such a future with AI assistants? It's something that you want to look at. By the way, although I look mostly at the behavior, sequential behavior kind of a scenario, I also want to point out that the same idea, as I said, essentially, in the case of one-shot decision, essentially, you can still talk about not just being accurate, but also making sense to the humans in the loop when you make mistakes. One of the biggest ways people lose trust in the machine learning systems is not when they are right, but when they are wrong, and they are egregiously wrong. And so not all failure modes are created equal. And so you may want to learn what sort of failures people are less likely to, more people consider more reasonable. And so, for example, we have done some work which shows that if you also take into account the failure modes and the cost of different failures, they're not all correct, the same cost. If you take that into consideration and if you assess that, that is sort of assessing an MRH. And then you would then use that to actually improve classification accuracy that people are happier with when you make mistakes. Because typically people get mad when you say that a school bus is an ostrich, right? So if you say a school bus is a Volkswagen Beetle, that's okay, because that's somewhat closer. Certain kinds of errors people get much more unhappy with. And so you want to realize the expectations better. And that we have done that. So the last thing I just want to mention and end right now is, what if the vocabulary is also different? This is like an important thing. We have focused often, on scenarios where the models may differ in terms of preconditions, effects, abstraction level, etc., but tend to have the same vocabulary, especially in scenarios when you have systems learning their own inscrutable representations, such as neural networks and so on. Then this part doesn't make sense. So you basically don't have a shared vocabulary. But as I mentioned to you, and so in those cases, in machine learning, it's been the case that people have essentially, XAI has become hard, but mostly as a debugging tool for inscrutable representations. And they focus mostly on pointing explanations. And as I mentioned from the beginning of this talk, pointing explanations are primitive. Civilization advanced because we went out of pointing explanations to develop and exchange explanations in symbolic vocabulary. And explaining decisions for sequential decisions would involve pointing over space-time tubes. And that's actually very hard, both in terms of doing and in terms of cognitive load on the receiver. So in a sense, in fact, those of you who are into saliency regions and pointing explanations, my thing for you is ask your friend, if some of you know that this school bus with this adversarial noise becomes this, which is actually an ostrich, according to most machine learning systems. The question is, then you ask the machine learning system, show me the saliency region on this that makes this an ostrich. What will it say? It's at most going to show some small, arbitrary, disconnected regions of pixels that wound up being important for it. And that make no sense to you whatsoever as an explanation. So keep that in mind. So again, as I said, as I mentioned, the right way to do is pointing explanations. We want to go out of pointing explanations, even if the tasks are tacit, and even if we have only inscrutable representations, by learning local symbolic models and exchanging explanations in terms of that. This is sort of an important thing to keep in mind, that there's a lot of talk about neuro-symbolic models and why machines should use symbolic reasoning. Actually, it's not clear that machines have to use symbolic reasoning for their internal efficiency. But they have to use symbolic reasoning to provide explanations to humans in the loop, at least until the point where humans have USB connectors and they can just sort of exchange representations without any actual talk. So the real reason for neurosymbolic explanations is you want to get out of pointing explanations and want to provide symbolic explanations. And so we have been doing nice work, what I think is nice work by Sharath, on handling different vocabularies by mapping explanations to concepts understood by humans, where we allow the machine to do its reasoning in whatever inscrutable representation it has. But when there is a foil presented by the human, in the vicinity of that foil, it essentially computes a symbolic model in terms of some common vocabulary that has been pre-decided, basically saying the humans might say the following concepts I understand, and the machine figures out when those concepts are holding true in the space-time tube in front of it. And then it provides the explanation of the space-time tube annotation, not as an annotation, but in terms of these symbolic constraints, such as missing preconditions and effects. There's a nice paper in ICML 2020 that I would encourage you to look at that tells you how to do this. Some work by Bean Kim et al. In Google doing what's called the conceptual activation vectors, TCAV, does the same sort of a thing, except for one-shot or single shot classification tasks. So that's basically where the symbolic explanations still will be the right way to go, except you will have to learn the symbolic models. So I won't have time to go into how we do the symbolic explanations. As I said, there's a paper on that. And as I said, this is not meant to be a fully technical talk. There's a different technical talk that you can look at. But I'm hoping that much of what I did here gave you some idea of how the different areas look at these explanations. One last thing before I show the summary slide is, here is some other work that we recently did, which is in the context of reinforcement learning, deep reinforcement learning. When the humans want to provide advice to the machines, they again would like to provide symbolic advice that needs to be converted by the machine into its own space-time annotations and then use it to improve its performance. So this is explanation augmented feedback in the human in the loop reinforcement learning. And that winds up, basically using the same sort of local symbolic vocabulary to allow for teaching from the human. In summary, multiple types exist in explainable AI with different interpretations of explainable AI. Explanations can be thought of in terms of mental models. I think that's the right way to think about them. The three-model framework provides a unifying view. The differences, if you are reading an XML XAI paper and it doesn't have three models, you should just ask themselves, how are they burying some of these models? Either they have sort of assumed away some model, or they have assumed that that model will always be constant, as I told you earlier in one of the slides. And whatever other motivations may or may not hold for neuro-symbolic AI, one thing for certain is that explanations are best exchanged in symbolic form. So our machines, I don't know how they need to reason, but they need to talk to us in language that we understand. And so for that, they need to understand symbolic reasoning and symbolic explanations, even if their internal reasoning is different. So I'll stop there. I am sort of seem to have taken quite a long time, but if there's any time for questions, I'll take them. And if you have questions on the chat, I can also answer them after this.
So there are Rob, there are a few questions in the chat window. We have actually gone into the next speaker's time, actually. So I also have a lot of questions. Maybe I'll mail them to you or whatever. But if you could spend some time and answering the questions in the Q&A panel, that would be great. And thank you for a wonderful talk. I'm sorry that I can't take any questions from the panelists right now, but this was really great. And thank you for this new talk.
Thank you.
Arun, you want to take over?
Sure, Ravi. Yeah, I will. Okay. So may I request Aditi to